So our next example, we have an OR situation. 6x minus 4 is less than 2x, or negative 3x is less than or equal to negative 9. So start doing the same thing and solving the inequality for one variable. We can start with this left one. Our first step here would be adding 4 to both sides in order to cancel out this minus 4. So adding 4 to both sides will cancel it out on the left hand side and leave us with the inequality 6x is less than 2x plus 4. We then want to get our like terms on the same side, our x terms, our two variable terms, so we'd want to subtract 2x here to cancel it out, and we'd of course have to do the same on the left hand side. So subtracting 2x from both sides, we end up with 4x, 6x minus 2x gives you 4x, the 2x minus 2x, those will cancel each other out, and we're left with just a 4 here. Last step to get x by itself, divide on both sides of that inequality by the coefficient 4. So dividing by 4, that will cancel out the coefficient, give you 1x, or just x, and on the right hand side 4 divided by 4 is 1. Okay. So solving one of those inequalities, we get x is less than 1. We can go ahead and graph that in order to look at the first graph to see what we're going to have here. So x is less than 1, that would look like a parenthesis around the 1, and anything less than that would be to the left. So shade in, including the arrow. Okay. So again, that's the graph of x is less than 1 there. Solving the other inequality, can do that pretty easily. Negative 3x less than or equal to negative 9. All we have to do is get rid of the coefficient. We do that by dividing by that exact coefficient, negative 3. That will cancel out our negative 3's over here, giving us 1x, or just x. And then negative 9 divided by negative 3 gives you a positive 3. But we did divide by a negative, so we do have to flip our inequality symbol. So it's x is greater than or equal to 3, not x is less than or equal to 3. So we can come down here and graph that inequality. The x is greater than or equal to 3. So what that would look like would be a bracket on the 3, and then shade everything to the right, because it's greater than 3, not less than 3 in this situation. Alright, so there's our two graphs. Now we have to take into consideration the word in between them, an OR situation. That's a union. Going back to the notes that we just did on the other page, the union now is when we're going to combine our two sets. We want to take all the elements from both sets. So if we were to take this graph and combine it with this graph, what would we have? There's nothing that overlaps between the two. So we would just end up having a graph that would have this piece on it and this piece on it. So if you actually were writing the answer, we'd have to combine the two sets. So let me kind of draw that in over here. So again, it is an OR situation, so we're going to combine the sets. So at positive 1 here and at positive 3 here, we would have the parenthesis shaded to the left of positive 1, and at 3 we would have the bracket, everything shaded to the right. That's what we would get if we combined these two sets. We would just have the same two graphs side by side, but nothing in between them. I guess we could draw in here that this would be the number 2 in between. And now how we actually write this in interval notation, because it's not one strict interval, it's two separate intervals. We write this as the first interval from 1 all the way to the left, well, we would write that as negative infinity to 1 with a parenthesis. The second interval from 3 to positive infinity, that would have a bracket on the 3, parenthesis around the infinity. And then because it is a union, it is an OR situation, we put a U in between the two, denoting that it's the union of those two sets. And that would be how you would write it in interval notation. Okay? It's a little bit trickier when you have situations like that. Alright, moving on. Our next OR statement has negative 4x greater than or equal to 8, or 5x is less than or equal to negative 15. So go ahead and solve these. You can do that in one step here. Divide by the coefficient to get x by itself. So we're dividing by negative 4. And when we do that, we have to flip the inequality, and we get x is less than or equal to negative 2. Cancels out the negative 4. Flip the inequality to give you x is less than or equal to negative 2. The other inequality, divide by the coefficient, which on this one would be a positive 5. That cancels out the 5s, gives us x just by itself. We're not dividing by a negative, so we don't need to flip the inequality. Even though we had a negative 15 here, we're not dividing by a negative. So we get a negative 3 when we divide, but we didn't divide by a negative, so the inequality symbol does not flip. But the 5s do cancel each other out. So here we have x is less than or equal to negative 2, or x is less than or equal to negative 3. So, excuse me, we can graph those. Over here, x is less than or equal to negative 2. Well, that would be a bracket at negative 2. And then everything to the left. X is less than or equal to negative 3. That'd be a bracket on negative 3. And then everything to the left. Remember, we have that OR situation, so we don't have to see what's in common, but rather we're saying what do we get if we were to combine the two sets. So if we were to combine the two graphs that we have from negative 2 onto the left and from negative 3 onto the left, well, putting those two together, combining them into one graph, we would take everything from negative 2 onto the left. So really all we need on our graph is maybe negative 2, negative 3, negative 4. Okay. Or remember, it's not an intersection. It doesn't matter where they overlap. It's more so if we added this graph to this graph, what would the result be? And the result would be this graph here. Everything from negative 2 to the left. You see now this is one single piece. It's not like up above where we had two separate pieces. And that's why we needed two separate intervals when we wrote in interval notation. This is one single piece from negative 2 all the way to the left towards negative infinity. So we can write this in interval notation then as negative infinity on to negative 2, bracket on the negative 2. Okay. So there's our graph answer and our interval notation answer. And then we just have one more. example and we'll be done with 3.2. So our last example is solving the inequality, the compound inequality x is less than or equal to -3 or x is greater than or equal to -5. We don't have any solving to do, we just have the basic inequalities. We can go right to their graphs. So let's do that. Graphing the first one, x is less than or equal to -3 would be a bracket on -3, and then graphing everything to the left. X is greater than or equal to -5. That would be a bracket on the -5, but it's a greater than or equal to, so graph everything to the right. Again, that was the graph of x is greater than or equal to -5. So, it is an OR situation. So, just like the last two, we want to combine our sets. We want to combine our two graphs. And if we were to add them together into one single graph, what would we have? Let's draw that in. Think about our one graph. I guess the important numbers are -5 and -3. Thinking about our top graph, the red graph here, that has everything from -3 to the left. I'm just going to draw it in pencil for now, but it has all of this from -3 to the left, including the arrow. The bottom graph, the purple graph here, includes everything from -5 and to the right. So all this, including the arrow. So if you kind of look at those two graphs together, it actually includes every possible number on the number line, from the -infinity all the way to the right to the +infinity. So combining the two sets would just give us a graph that had everything filled in. Everything from -infinity all the way to +infinity. And we don't need the brackets on the -3 and the -5, because by filling it in like I just did, it implies those those values are included in the graph. So everything on the number line would be shaded in, including the arrows. How do we write that in interval notation? If you recall, everything being included means we have everything from -infinity to +infinity. Infinities always get the parentheses. And then there's another way we do say that, and that is all real numbers. And they could be pretty much anything. And that concludes everything for 3.2.